My name is David Rolfe. This is really Yes, definitely. Anyway, there's not that many people here. I'll just speak loudly, which is what I normally do anyway. I use my annoyed in restaurant voice. I'm here from VoltDB. We're based in Bedford, Massachusetts. We're a high-performance online transaction processing database that is memory-centric. Hence our presence here at the In-Memory Summit. I'm going to talk this morning about intelligent ingestion, the idea of how you get lots of stuff into your database to take decisions very quickly. It's somewhat opinionated, somewhat informal, probably won't run for an hour or 50 minutes, so you don't have to panic. My colleague Tom at the back there has a sign-up sheet for anybody who wants further information or wants to speak to us at some point in the future. I'll be available for questions afterwards as well. And with that, I'll start. In order to understand where we are now, you have to look at the past. And a lot of what the world we live in was defined by the mid-1980s, because around 1985 is when the first generation of database products were designed and came into the marketplace. And it was a wildly different world. The economics of it were completely different. The smallest computer, the IBM PC, cost about $3,700. And in computing power, you can get considerably more intelligent light bulbs now. Single multi-CPU computers didn't exist, and there was very little computer-to-computer communication. That only kicked in much later. So what came first? First came the realization that data was valuable. The database came about because everybody had stuff on tapes and was feeding tapes between programs, and it was driving everybody mad. And companies like Oracle and IBM and Sybase realized that there was money to be had in marketing a central repository for everybody's data. Because before that, I started my career at the very end, the very, very end. My first summer job was as a computer, was euphemistically described as a tape monkey in the data center. It was my job to hang tapes. And the realization that there's literally hundreds of tapes being generated and used every night, and there's no easy way for any piece of code to see any piece of data anytime it wants, was one of the big drivers for this. So the era of the database arrives, and the first thing they come up with is it's very bad practice to let use cases dictate the data structures. Anybody who ever went to any traditional late 80s, 90s database class will tell you that the schema is all important, the structure of the database what matters. It's the only thing that we really care about. And if you have to optimize, you've done it wrong. It was as a repository. In fact, the ultimate goal we were aiming for was one database. That's why there was so little time and energy spent on figuring out how to get databases to speak to each other. Because companies like Oracle, IBM, and Sybase and all that, and Microsoft, were saying, well, there's going to be one database and all your stuff fits in it. And it was really being heavily pushed. And with hindsight, that was all a bit Soviet. The one big database, the central thing. And we've seen the reaction to this. And now we're in a world of microservices and lots of individual little databases. But before we laugh at it, we have to consider that the one big database need came about for some pretty good reasons. There was absolute chaos in data processing before the database arrived. And to a certain extent, we've gone back to that, because we've now got about 100 separate kinds of database out there. Developers are quite freely managing their own data all the time, and now we're seeing a lot of the friction which historically had started to come back. So we're probably seeing a reaction that go back to roughly somewhere in the middle. But one of the things did stick. So one of them is the fact that the data is more important than the use case. Long term, if you look at what companies like Facebook, what's valuable to them is their data, not their application. And so the whole one big database idea was killed by arguably office politics and complexity, because one of the big barriers to having one big database is there'll be multiple internal constituencies, all of whom have their say, all of whom have their budget, may have conflicting objectives, and may even be trying to exterminate other parts of the organization. It was also too complicated, and the reality was in the late 80s, early 90s, there were no products available to do that. And virtualization. When it used to be that having computers in the office was quite rare, now everybody has one. A few years ago, I was on site at a company which was Borland's headquarters, and somebody said, "Oh, do you have any spare PCs?" And the guy said, "Yeah, about 40." Right? And he said, "40 PCs?" He said, "No, 40 pounds PCs." So there's so much spare hardware lying around that technologies like Hadoop and lots of distributed systems kicked off simply because it was available and anybody could develop. And so, but let's move forward, because I'm rabbiting on about the past. The things we're trying to do now are fundamentally more complicated. So let's just say we have an application that wants to predict flight delays. Now there's several interesting examples of machine learning where they take, in the US this is freely available, you can get with the front list of every flight, how late it was, and what they think made it late, and all that stuff. And you can run it through machine learning algorithms, and it will come out and it will tell you, oh, I think this flight between these two cities on this day of the year is probably going to be late. Well, that's all reactive retrospective information. If I want to do this in real time, because I'm cool and I want to make money out of it, this is what I would do. First, I need scheduling information. That's easy. That's known years in advance. Then I need the weather. That's a big issue. Weather forecast. I need to know the weather for today. I need to figure out how that's going to impact my day. I need to know whether a particular flight is full or not, because full airplanes are far more likely to lose space. I need to know how much. Now it gets complicated. I need to know how long the crew agreement is, because there's a possibility that if you get delayed more than a certain amount, you hit 11 hours or 12 hours, whatever the limit is, they can't fly anymore. Well, it has to people in the crew who've been on business trips and have the airplane go back to the gate because the crew cannot get to the destination and be away. Then there is basic things like do you want to just use the wide one for now? The first 10 minutes of this there'll be no sound whatsoever, so that's going to be hilarious. No, I tried it and it was absolutely deafening. Okay. Is that less deafening? Okay. Right. So the next thing you have to find out, this is going to confuse people for years. I mean, look at the first 10 minutes of this and they have no idea what's going on. Is which part of France is shut today? Because that affects your journey. And I love this one. I deliberately use Comic Sans because I think it's the most ludicrous excuse in the history of mankind, the late arrival of the incoming aircraft. I mean, if I want to do this cheaply, I just keep track of where the plane I'm supposed to be on is. And I could probably get 80% accuracy just with that, if it's late or not. But the point I'm making here is, at one level, I can do this with one data source, a historic list of flights, and make a guess about what's going to happen next. But if I want to do a good job, I have to bring together a whole series of real-time data feeds. And these are feeds which are changing all the time and will become out of date within a couple of minutes. And this is where we get to the whole idea of intelligent ingestion and taking decisions as you go along. And this is where I go off. Anybody who's ever, there's lots of military officers running around talking about this stuff, the OODA Loop. And there was an American fighter pilot, a guy called John Boyd, who invented this, and the military use it, and it's relevant to what we're doing. The idea is that when you're taking decisions, there's 4 steps. There's observe, figure out, see what you can see. Orient, which means looking in your context, in how you see the world, what does it mean? And when you've established what it means, you need to take a decision, and then you need to act, and then you go back around in a circle. And his key piece of idea was if you can do this faster than the other guy, or the environment you're in, you can start to take over it. If you can't, it doesn't matter what your capabilities are, you'll still lose. So his nickname was 40-second Boyd, because having done all this and having done a lot of research on the capabilities of different planes, he could consistently get behind somebody, no matter how good they were, in 40 seconds or under. And so, how is this relevant? If you want to, in any kind of real-time situation, you have to be able to reach conclusions about what to do and act faster than the situation is changing underneath you. With a web page, that's about 7 seconds, because that's how long people are willing to wait for a web page, and human attention span is about 7 seconds.
If you're in the IoT, you now need to be doing this in around 7 milliseconds, potentially. We're in a different ball game. We're all in the right room. You need to be in an in-memory database summit if you want to do things in 7 milliseconds. But winning now involves taking complicated decisions, gluing lots of stuff together really quickly, and doing it consistently and reliably, and in the GPDR universe in a manner where you can explain why you did it, because thanks to GPDR we can no longer take decisions and not explain to the customers how we did it, that took them. And this has been going on for a while. 1980s, taking 2 days for a decision was normal. Mid-90s, you were doing it in a couple of minutes. The year 2000, with web pages and then advertising, you had 8 seconds, potentially, to get an answer, to decide what advert to show. By 2010, we're now at video game analytics and starting to change the behavior of video games as they're happening. We are looking at sophisticated advertising where you have to go out and have people start bidding for things. And that's maybe 100 milliseconds. And meanwhile, the actual volume of traffic on the internet is skyrocketing. And now, 2015 to 2018, we're now talking the Internet of Things, 10 milliseconds. The 5G telco standard is talking about 1 millisecond latency. 1 millisecond is 186 miles at the speed of light, which means that you won't be able to have everything in one big data center. You're going to have to be in every town in America and every town in Britain for it to work. The number of things you have to look at, it's gone from a single row being looked at, potentially looking at thousands of things. We have customers in the video game space who do video game analytics, and they will watch somebody playing a game, and they have to keep them in a narrow corridor. If it's too easy, they get bored and go away. If it's too hard, they get frustrated and give up. So you have to watch their progress along the game and figure out how hard to make it slightly harder. Do we need to try, is this a really good time to sell them the proverbial dragon slaying shield? Because a lot of these games are trying to do upselling game. And these guys are literally looking at hundreds of data points in real time. And this is part of a much broader pattern. This is one of my favorite graphs. The cost of RAM, in 1985, a gigabyte of RAM was $7.5 million. It's now $7.50. And the reason we're all here, the reason there is an in-memory summit, is that technology has drastically changed. Everybody here in this room is on the side of Moore's Law and is surfing Moore's Law. And that things which you used not to be able to fit into memory, you now can. But in addition to that, the market and the expectations for what people want are moving much more towards environments where you have to have it in memory for it to work. So where are we? We're at a point in life where things are getting difficult. The timescales are proving a challenge. Volumes and complexity, they're all moving against us. So there's a lot of work that needs to be done here. We need to take decisions that involve lots of data sources. With traditional key value solutions, you could potentially be talking about a lot of trips to your store and back again. This is one of the arguments behind Volt, is that we want to reduce the number of trips across the network, because that's one of the things that's very hard to get rid of. If I need 100 pieces of data and they're in 100 key value locations, either I do 100 requests simultaneously asynchronously in an attempt to manage that, or I do one request which does all the work. We know that legacy RDBMS doesn't cut it because it was designed literally in the last century. And we're also looking at increased interest in aggregate decisions. How many people here have heard of HTAP or translytics? Anybody? Right. This is the Forrester Gartner thing, the new thing they've invented that you're supposed to be good at. And for people who haven't heard of it, it consists of being able to do transactions and count what's happening at the same time. For anybody who's worked with a relational database, I can write an application where I'm doing lots of inserts and updates all the time, or I can query the data instantly. I can't actually do both and get it to scale, because it's too much stuff is moving. That's one of the things we managed to do at Volt to solve that problem. But anyway, we also see that a lot of decisions now involve telling a third party something. The classic dilemma in OLTP was, I did the transaction between me and my client, but there's other parts of my organization that need to know what I've done, and I would struggle to tell them. So this is, what you actually need is the ability to combine all this stuff. And this isn't just a technology thing anymore. This isn't just, a money thing. You can't buy your way out of this. You need the right technology. This is where we come in, or where we claim to come in. Look, I'm a vendor. I have to do this. Vault architecturally is designed to allow you to do ACID transactions at scale in milliseconds. Lots of them, hundreds of thousands of them. Now, we do a lot less easily. And so our idea is that you can take complicated decisions involving multiple data sources while still preserving ACID. And what does ACID mean? ACID isn't something you necessarily need for bank transfers. Any operation that involves a bunch of reads and then a decision potentially needs it. Because if I have to do 50 separate reads to get an answer, the data could be changing underneath me. I could be taking wacky decisions all the time. And you need to be able to do it at scale and with millisecond timing. So the question I would ask is, why would you use us? Apology for the pitch here, the engineer. And the first thing I'd say is, we are designed to take decisions at scale that are ACID and are very low latency. I have seen database pitches, not for anybody who's here today, but for a couple of other vendors, where they attempt to position their new product as a magic solution for everything you need. It's, it'll solve everything. It's a Swiss Army knife of databases. We're not that. We're here to solve high-performance OLTP solve problems. You can use us for other stuff as well, but our sweet spot is that. And so the example I give is the Aerial Atom, which is a track car. If you're rich and you want to drive around race courses quickly, this is what you use. You don't use it for school runs or going shopping. And I'll give you a brief overview of how we do this. Traditionally, in college, you get taught that a database has 2 or more people making changes, and the job of a relational database is to stop person A from seeing what person B is doing until they've finished, and stop person B from seeing what person A is doing until they've finished. That's what turned into a $35 billion industry. And the model you're shown in college is a couple of people, a CPU, some RAM, and disk. That's how it started, but this worked reasonably well until you started bringing in other CPUs. Because it's one thing to keep track of users and making sure that user A can't see what user B is doing, and vice versa. But when I've got multiple CPUs, each of which could be at the same moment in time taking decisions, I now need to have to make sure that they can't see what I'm doing, and they're not allowed to break things. So you've got this sort of orthogonality thing going on, where at the one level you're trying to make sure your users can't see each other, and at the other you're trying to make sure that the other parts of your own system can't see it. As you scale, this goes to hell in a handbasket. Because we used to have single CPU databases, then we had multiple CPUs on 2 separate servers, and now we've got 2 16-core boxes. So there's 32 threads of activity attempting to do work in real time right now. And there might be 1,000 users. So the number of possible ways this can go wrong starts to escalate. And this is why Michael Stonebreaker, who thought up Vault, said, hang on a second, how much time are we spending on just simply keeping track of who's doing what? And he did some academic papers, as he does, being an academic, and he said, well, in a traditional database, buffer management and logging, interacting with disk, is half of all the CPU time. It just goes on that. Locking and latching, which is the process of lying to each other about who's doing what, took up another 30%. And this was why it wasn't scaling. The more people you add, the worse it gets. The more people who are involved, you just see a classic law of diminishing returns kicking in. And so to go from 1,000 transactions per second is a question of disk. 3,000 to 4,000 transactions per second, you might need a second server. Anybody who's worked with legacy technologies for scaling would know that adding the 3rd server in a traditional legacy database does not give you a 3rd more transactions. And so he said, how do we solve this problem? And he said, well, if you looked at how we build databases traditionally and tried to run a supermarket like this, it would be a supermarket where I could walk up to the cashier, put some food down, walk off. Cashier is sitting there wondering what to do because it's an incomplete transaction. They start to do somebody else's work. I come back, put something else on the conveyor belt. And this is traditionally how we would do things. And the problem with that is it doesn't scale. So what we said was, okay, we're going to do a couple of things. Firstly, we're going to, for high performance transaction stuff, we're going to insist that you partition it by some aspect of the data. Secondly, we're going to use stored procedures as our primary means of doing work. And the reason is, the stored procedure either finishes or it doesn't. We do not allow transactions to continue running in between calls to the database. This is a big change from how we do things historically. The whole idea of doing a row-level lock and having the client sitting there is based on the assumption that a human is sitting there going, stroking their metaphorical beard and waiting to take a decision. If you look at who our customers are now, they are other computer programs, they are IoT devices, they are internet standards, they are things where a decision needs to be taken and there is no, and what they want is a really clear answer as fast as possible. They do not want the opportunity to change their minds. There are cases where that is the case, but the vast majority of stuff we're seeing, we have a lot of success in the telephone industry, where the question is, do I have enough credit to start this call? That's a simple question. And then the next thing is, please give me 10 units of credit and I'll come back to you in 2 minutes. That's the kind of thing we're dealing with here. So what we're saying is, we partition the data. Your request is the beginning and end of a transaction. The transaction takes place on the server. And we're queuing it up by core. Why would anybody partition by core instead of server? On an 8-core box, it doesn't matter how many threads I create, I can only do 8 things at once. It's not physically possible to do more than 8 things at once. So instead of living in a world where we pretend that all resources are free and infinite, we accept the physical reality. We say, okay, I'm going to have 1 thread per core. It's going to be a single thread, and it's going to be doing the entire request one at a time. This is how early versions of Sybase worked, by the way. The advantage of this is that because we don't let 2 transactions for the same partition run at the same time, there is no locking issue. There is no visibility issue. You are never both there at the same time. There's a tiny penalty to pay and induced latency, but the reality is it really is not only tiny, it's pretty much illusionary because there were only 8 cores. You weren't going to run faster somewhere else most of the time. And what we find is that we are about something between 8 and 15 times faster than a traditional RDBMS based on observed tests, and provided you accept the caveats that we don't allow transactions to last beyond calls to the database. This is how a supermarket works. And so what we're doing is how a supermarket works, in that you are forced to queue up at a cashier. You are not allowed to put your stuff down, start your transaction, and go off and go shopping again. You can try it, people get really mad. And to hammer home this point, I apologize, there are only 3 ways you can actually interact with any database. So you can go the traditional route, which is lots of SQL statements, which is how the standard evolved, and developers like it because they feel in charge of it. It fitted the 1980s paradigms of people looking at PCs and screens, deciding what to do next. The transaction volumes were so low it didn't make a difference. But it doesn't scale well because you've got people locking things. There's questions about who locked what in what order. You now have problems with application servers. If I had 800 PCs speaking to a server and 1 dies, that doesn't matter. One of the PCs dies, that doesn't. If I've got 800 PCs speaking, or 800 clients speaking to 2 application servers speaking to a database server, and one of the application servers dies, and it's locked a bunch of records, you are now in a world of hurt. Because the clients will come back, will attempt to use the same resources, and they are now locked by something which is dead. The KV, the key value store people, they say the database doesn't care what it stores, we just store a key and a value. It demos well, it's good for simple applications. As scale and complexity goes up, you find you cannot use 1 key value pair to solve your problem. You now have to manage interactions of multiple of them. That turns into things like multiple network trips. It turns into things like ACID issues, because, okay, if I have to read 40 pieces of information, then create 1, the acidness applies to 41 things, not 1, because the decision I'm making is based on assumption that I had a particular read at a particular time. Which is why we're using stored procedures. Now, the problem with stored procedures is that thanks to PL SQL, they are about as popular as certain world leaders. But we get predictable speed, we get very high performance, and we have really good scaling characteristics, which is why we do it. So, to give you an example of the kind of thing we can do with this, because we use Java as a stored procedure language, now we have a Java layer, and then you go into C++, which is where the data lives, which is so we don't have any JVM garbage collection issues, in case anybody's wondering, because the moment I say Java and stored procedures, somebody puts out their hand and says, well, what about garbage collection? For machine learning, it really is, peak machine learning at the moment. Everybody is talking about it all the time, but we have to have a reality check. It adds value when you combine it with state. To go back to the earlier example of airline flight delay prediction, I can go off a big historical file of flights, or I can build an application which will tell me what's going to happen to your flight today. And in an ideal world, would book you onto something else because we know there's going to be a disaster. It has to be used to take some kind of decision. I mean, the number of vanity machine learning projects where people discover utterly useless facts. At the end of the day, we're all here because even if we don't want to make money, our bosses do. And if our machine learning projects don't lead to an improvement in the bottom line, at some point it will quietly go away, and we might as well. So we have to be realistic about what you can accomplish. And it has to happen in real time. This whole point of this meeting, the whole idea of in-memory, is that we're doing things in real time. We have a phrase at Volt, influence the moment. We're trying to influence something which is still happening. It goes back to the OODA loop, it goes back to everything else. And that means that I can combine data from lots of sources really quickly. And this being 2018, we're assuming we can do it at scale, which comes back to our diagram. For those of you who care about machine learning, we have demonstrated our ability to work with pretty much any machine learning engine with a Java runtime. So what's interesting is you can develop your model, and if you can express it in Java, you can run it in Volt. The limitations we have will be with instantiation. Some machine learning models, like JPMML, for example, it takes 700 milliseconds to start the engine. It then takes about half a millisecond to do a request. So you wouldn't want to be starting that every request. And why would you want to do this? Machine learning, it's up to its eyeballs of people generating models at the moment. Everybody is fixating on the model. Here's my model, here's my model. How do you use it in reality in a computer system? Because if it's got some weird protocol, if it's got some weird language, or they've built their own machine learning engine which isn't transactional, can't store state, and if my goal is to improve people's lives by influencing the moment, I need to be able to combine their state with the machine learning engine. And so that's something we're seeing that good at. Weaknesses, I think this would probably apply to most technologies, never mind Volt. If the runtime engine has runtime dependencies on another server, things like latency and HA could go out the window. It has to be deterministic. That's Volt especially, but most technologies. And if it's not fast, then the question is why you're doing it. This is where the material gets a bit esoteric and technical, so I apologize. This is an example of how you can create, using H2O, we created a model using the airline example earlier, and we created a Java class, which simply takes in the flight number and a bunch of other details, runs the model, and then returns the results. Now, what use is this to me in the database? The answer is I can turn this into a Volt function. That is possibly the most impressive single line of SQL DDL I've seen in years, because it means I can now access that as a SQL function. I can issue a query, that's an actual example, where I can pass in the flight number. I create a procedure where I pass in the flight number, and it will run the function and give me the results. And we're running this comfortably on a laptop, 10,000 transactions per second. And this is other people are talking about it, we're doing it. This is a dreadful slide. If people want to see stuff demoed, I'm happy to do it afterwards. It's not great material for the size of the room. And it's just basically an example of a Volt store procedure where it starts up here. And what we do is we do a couple of sanity checks to make sure we haven't been given crap. And then we go off and we run an engine and we return results. And so that's what it would look like. Yeah. And just in case anybody's wondering, we are doing this for real. Huawei are using us in China for credit card fraud prevention. The way it works is if you were in China, they have a gigantic Hadoop data lake that describes all of China in terms of finance, in terms of fraud, in terms of retail outlet. They apply demographics and tags to their customers. And when you walk up to a retail establishment in China and you try and swipe your card, it will apply something like between 100 and 200 rules, all in Volt, all in Java, and come up with a score saying whether we think this transaction is plausible, whether we should approve it. And it does that in about 37 milliseconds. And the beauty of this is they're regenerating the model 6 or 7 times a day, because the problem in credit card fraud now is there are gangs out there who are moving between towns, who are changing their behavior all the time. So you can't do last week's solution for this. So what we're seeing is that so the interesting thing, so it's a really interesting example of machine learning being used in reality for something which is commercially relevant. I think I've gone to my last slide, which is just say that we have lots of companies who are seeing the value we provide. And at this point, I'll stop for questions and give you 10 minutes back.